Welcome to The Explainer. Today, we're diving into a concept that honestly feels like pure magic, but is actually governed by some of the strictest rules in physics. We're talking about wireless power transfer. We all share this sci-fi dream of a completely untethered world where electricity just flows through the air, right? As seamlessly and invisibly as Wi-Fi. But when we look at the reality of modern technology, there is a massive contrast between that century-old dream of global wireless energy and the actual rigorous engineering required to make it work today. Okay, let's dive into this. Because it really is the central mystery of wireless energy. We can effortlessly drop our smartphones onto a charging pad, and we're now even charging entire electric vehicles wirelessly. So why can't we just broadcast power to our homes through thin air? Why are we still relying on literally millions of miles of physical copper wire to keep our world running? Well, to understand why, we've got to look back at the original vision. A user on a Reddit discussion actually summarized the concept brilliantly. They said, it's as if all of human society was placed inside a microwave oven operating at low frequency. Imagine that for a second. If you held up a fluorescent tube in that kind of environment, it would just glow on its own, wirelessly, anywhere on Earth. It paints such a vivid picture of a world completely saturated with ambient usable energy. Section 1. Tesla's wireless power dream. That brings us to the legendary inventor who started it all, Nikola Tesla, and his massive ambitions for the future of electricity. Back in 1901, Tesla began building the Wardenclyffe Tower, and his idea wasn't just to shoot radio waves through the air. He actually recognized that standard radio waves lose power way too quickly over distance. So instead, he wanted to use the Earth and its atmosphere as a giant capacitor. By vibrating the electromagnetic field at the exact resonant frequency of the Earth, he thought he could literally pump energy into the ground and let anyone, anywhere, just extract it. It was a wild idea. But unfortunately, the physics of radiative losses and the harsh reality of extreme power dissipation meant this incredible vision was ultimately mathematically impossible. So to understand exactly why Tesla's global dream hit a brick wall, we have to look at a fundamental boundary in electromagnetism. It's called the radiant sphere. If you look at the mathematical boundary here, it literally separates all wireless power into two completely different physical camps. Inside this boundary, energy is stored and reactive. It acts almost like a contained bubble. But outside this boundary, the energy detaches and radiates away into space as a wave. Section 2. The near field, close contact. Let's look at this first camp, which is the tech we interact with most in our everyday lives. So the crucial point is that near-field power doesn't actually radiate energy out into space. Instead, it uses magnetic or electric fields to create this contained bubble of stored energy right between a transmitter and a receiver. And because it doesn't radiate, it is incredibly safe for humans, plus it doesn't cause massive radio interference. But there is a brutal trade-off here. The field strength drops off at the inverse cube of the distance. Literally, if you move your phone just an inch off the charging pad, the power transfer collapses completely. But when you do keep things close, the results are absolutely staggering. Modern resonant inductive coupling, which is exactly what's being deployed to seamlessly charge electric vehicles in garages right now, can hit grid-to-battery efficiencies of over 90%. By tuning the magnetic fields to a shared resonant frequency, we can push massive kilowatts of power across an air gap almost as efficiently as plugging in a physical copper cable. It's amazing. To really grasp the whole wireless power landscape, we have to compare the two methods head-to-head. Near field relies on magnetic or electric fields over tiny distances. We're talking millimeters or centimeters. Far field, on the other hand, uses propagating waves, like microwaves or lasers, to cross kilometers of open space. You really cannot treat them as the same technology. I mean, a near-field toothbrush charger and a far-field space laser operate on entirely different physics. Section 3. The far field, radiating power. Which leads us to the tech that finally allows us to beam energy over those vast distances. But as you'll see, it comes with immense technical hurdles. If you want to beam power across a valley, or say down from space, you use microwave power transfer. It's a three-step process. First, you convert direct current electricity into radio frequency using high-power amplifiers. Next, you use antennas to focus and shoot that beam right through free space. Finally, on the receiving end, an array called a rectenna, which is short for a rectifying antenna, catches those microwaves and converts them back into usable DC power. Now, what's really interesting about this slide is the massive drop in performance compared to near-field systems.
Despite some seriously incredible engineering, the end-to-end efficiency of far-field microwave systems currently sits below 40%. You lose energy converting it to radio waves, you lose more as the beam travels and spreads through the air, and you lose even more converting it back to electricity at the end.
And the biggest culprit for all that energy loss? The inverse square law. Unlike a laser pointer, an electromagnetic wave spreads out as it travels. So by the time your beam reaches a target a kilometer away, the energy is heavily diluted across a massive area. To actually capture a meaningful amount of power, you either need to perfectly focus the beam with huge, highly expensive antenna arrays, or you just have to accept that most of your beamed energy is going to completely miss the receiver. Section 4. The Great Efficiency Trade-off. This brings us to the core dilemma of modern wireless power engineering. Every time you increase convenience and distance, it physically costs you energy. When we evaluate these side by side, the trade-offs are super clear. In the near field, inductive methods give us high efficiency, but if those coils misalign even slightly, power plummets. Capacitive near field uses lightweight metal plates instead of heavy magnetic coils, but it needs dangerously high voltages that risk electrical arcing. Moving over to the far field, microwaves can travel kilometers, but suffer from that sub 40% efficiency due to beam diffraction. And lasers? Well, they solve the diffraction problem with tight optical beams, but they have the lowest efficiency of all, often under 30%. And something as simple as a passing cloud or heavy rain can block the power completely. When we scale these technologies up, we run into a major hurdle that experts call the efficiency tax. Think about it. For a single driver, a near-field EV charger might only be 5 to 7% less efficient than just plugging a physical cable into the wall. You'd barely even notice that on your monthly power bill. But what if millions of vehicles are using wireless chargers? That 7% drop suddenly represents gigawatt hours of wasted energy on a national scale. Utilities and policymakers have to carefully plan for this massive extra load on our smart grid. Notice that small gap between the wired conductive charging bar and the wireless inductive charging bar. That gap right there represents the physical cost of cutting the cord. It's a slight drop, sure, but a highly impactful one when applied to heavily energy-dependent infrastructure. And this brilliantly illustrates the current economic reality of wireless power. For an average consumer buying a wireless car charger, it costs more upfront and wastes a little bit of electricity. It's essentially a convenience premium. However, if you're running a commercial fleet of autonomous warehouse robots or city transit buses, wireless charging actually saves you money. It completely eliminates manual labor, prevents connector breakages, and allows vehicles to carry smaller, lighter batteries because they can just charge continuously throughout the day. Section 5. Powering the Future. So, with all these physical limitations and efficiency taxes, how on earth do we push this technology forward? Well, the answer lies in how we control the power. Instead of relying on perfectly aligned hardware, modern engineering is leaning into artificial intelligence. Companies are integrating machine learning algorithms that monitor the connection hundreds of times every single second. So if a drone lands slightly off-center on a near-field pad, the AI dynamically tunes the electrical impedance in real time to maintain peak efficiency. And in far-field systems, AI controls arrays of metamaterials to instantly steer and focus microwave beams onto moving targets, which completely bypasses those traditional misalignment issues. Let's move to and see how this builds into some absolutely jaw-dropping real-world deployments. Companies like Reach Power and Wybotic are making the untethered world a reality right now. We're looking at military drones capable of endless flight, just hovering while receiving power beamed straight from the ground. We have factory floors where entire fleets of robots operate 24/7, continuously receiving optimized power without ever needing to plug in. We can drop unattended sensors in extreme environments that run forever without a single battery swap. And on the horizon, the ultimate application, harvesting solar energy in space and beaming it directly down to Rictena farms on Earth. No way, right? But it's happening. So what does this all mean for us? The physics of the radian sphere and the inverse square law tell us that wireless power will never be 100% efficient. But as AI continues to close that gap, we are left with a pretty profound question. As our world becomes increasingly automated, is the efficiency tax a small price to pay for the ultimate convenience of a truly untethered world? Thanks for exploring the physics of wireless power with me.